Good day, learners. Welcome to our physical sciences lesson. My name is Aminim Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11s, our focus today is on paper 1. So we are going to revise paper 1. Actually, for this year, we are done with the ATP. We have completed the ATP for paper 1 and also for paper 2. So now our focus is on exams. So today we are going to focus on paper 1 revision. And under paper 1, the knowledge areas that we are going to focus on is mechanics and electricity and magnetism. Right. When it comes to our paper 1 learners, I hope grade 11s are aware that our paper 1, it's physics, which is out of 150 marks, and then this is how marks are divided. You have your section A and your section B. So your section A, it's multiple choice questions, which is out of 20 marks, and then your section B, it will be the structured questions, which is out of 130 marks, and then 130 plus 20 marks, it's 150 marks. So that is our paper 1, right? So I want us to start with section A because, you know, in most cases, our learners you struggle a lot when it comes to answering, you know, the multiple choice questions. So today I'm going to give you, you know, skills on how to, you know, to answer multiple choice questions. And in most cases, you'll find learners leaving out, you know, question 1. So obviously, if you are going to leave out that 20 marks already, the chances of you failing, they're very, very high. So it's very, very important, learners, to make sure that you answer all questions when it comes to our section A or when it comes to our question 1, which is our multiple choice questions. Right, so when it comes to multiple choice questions, one of the things that is very, very important, learners, is please make sure that you read, you know, the statement given with understanding. Then from there you move to, you know, the options, because you cannot start with the options and then you go back to the statement, right? So what is important, make sure that you read the statement that is given with understanding, and then from there you can go to, you know, to options, all right? So another thing which is very, very important when it comes to multiple choice questions, so multiple choice questions, actually they cover all the concepts, right? Or all the knowledge areas or all the topics, right? Your knowledge areas, for example, when it comes to paper 1, you have your mechanics and your electricity and what? And magnetism. So the multiple choice questions, they will cover all those knowledge areas, right? So let's look at our 1.1. So if you look at our 1.1, it's based on Newton's laws and application, and actually the different kinds of forces, all right? So it's one of the topics that you did this year. So if you understand the different, you know, kinds of forces, then you'll be able to answer 1.1, right? So 1.1 reads as follows: which one of the following forces? So here we are talking about forces, right? So you know what is a force. Remember, a force is a pull or push. So which of the forces or following forces always acts perpendicular to the surface on which a body is placed? So for you to be able to answer this question, right, you must know all, you know, the different kinds of forces, the contact forces and the non-contact forces. So let's start there. What is a contact force? What is a non-contact force? All right, so you must understand all those types of forces, contact forces and what, and your non-contact forces. So for example, your contact forces, those are forces exerted by, you know, by objects on each other when the objects are in contact, all right? Then for example, your normal force is a contact force, right? Right, so your normal force is a contact force, and then your frictional force is also a contact force, and then tension is also what, a contact force. But C, it's a non-contact force, which is your gravitational what forces. So instead of, you know, asking about the force that always acts perpendicular to the surface. Here they will say which of these forces are non-contact forces, right? Then you must be able to answer that question, because we have a non-contact force there, which is option C, which is a gravitational force. And then the contact forces here, it's your normal force, your frictional force, and also your tension force. All right, so you have your normal force, you have your frictional force, you have your tension force. So these are contact forces. All right, and then you have your gravitational force, which is a non-contact force. A non-contact force, right? Then from there, define the normal force, define the frictional force, the gravitational force, the tension force. So remember, normal force, which I believe it's what you know by now, that is the force exerted by the surface, by the surface on an object which is in contact with, and it always acts perpendicular to the surface. The force exerted by the surface on an object that is in contact with, and it always acts perpendicular to the surface, right? Then you move to frictional force. So the frictional force, that is the force that opposes the motion of an object, and it always acts parallel to the surface. Frictional force, that is the force that opposes the motion of an object, and it always acts parallel to the surface. Please, learners, let's be careful when it comes to frictional force. It is not the force that opposes the force applied. It is the force that opposes the motion of an object. For example, if an object is moving to the left, then the frictional force will act in the opposite direction, which is to the right. If an object is moving in an easterly direction, then what is the opposite of east? It is going to be west, which means that the frictional force will act in the westerly direction. So it is the force that opposes the motion of an object, and it always acts parallel to the surface, right? Then types of frictional forces. We have a static frictional force. We have a maximum static force. And then you also have the kinetic frictional force. So those are types of frictional forces, right? So, but what is a frictional force? That is the force that opposes the motion of an object, and it always acts parallel to the surface. And then different types of frictional forces. We have a static frictional force, right? We have a maximum static frictional force. You also have the kinetic frictional force, right? Or kinetic friction, right? And you also need to know those forces, their definitions, right? Like your static friction. Static friction, that is the force that opposes the motion of a stationary object, right? The motion of a stationary object relative to the surface. So that is static friction, all right? Then you also have the maximum static friction. So the maximum static friction, that is the force that opposes the motion of a stationary object just before an object will start to move, right? So that is the maximum static friction, the force that opposes the motion of a stationary object just before an object starts to move. That is the maximum static friction. Then what about the kinetic friction? So kinetic, that is dynamic, right? So kinetic frictional force or friction, it is the force that opposes the motion, the tendency of motion of an object. The tendency of of motion of an object that is in motion relative to the surface. All right. So that is the kinetic friction. All right. So those are three types of of friction. We have the static friction, which is the force that opposes the motion of a stationary object relative to the surface. And then you have the maximum static friction, which is the force that opposes the motion of a stationary object just before an object starts to move. Then we have the kinetic friction, which is the force that opposes the tendency of motion of an the motion of an object that is in moving relative to what to the surface. Ne? Then we have the gravitational force, right? So that is the force exerted by the Earth on objects that are on or near its surface. So that is the gravitational force. That is the force that the Earth exerts on objects that are on or near its surface. So that is the gravitational gravitational force. All right. So which answer is correct here? So we can see that when it comes to this question, right, there's a lot that you can talk about. So what is important, learners, here, you don't just focus on the question. All right. So there's a lot that you can do with this question. One, you can categorize these forces as being contact and non-contact, and then from there give the definition of each force so that you'll be able to answer that question. All right. And then from there you can go back to to the question and try to answer that question. So which one of the following forces always acts perpendicular to the surface on which a body is placed? So here it will be the normal force. All right. So the correct option here will be what will be the normal force. It can't be frictional force, because frictional force, it always acts parallel to the surface. It can't be the gravitational force, because the gravitational force is always acting downwards, right? Okay. So then it can't be the tension the tension force. Right. Let's look at 1.2. So 1.2. When a spaceship moves at a constant velocity, so you need to underline the key weights. So constant velocity. It means that the resultant force acting on the body is 0, right? This phenomenon is best explained by, is it the Newton's first law, the Newton's second law, the Newton's third law, or the Newton's law of universal gravitation, right? So what is important here, you have to state each law in weights. All right. So your Newton's first law, your Newton's second law, and then your Newton's third, and also your Newton's law of universal gravitation. Right. So Newton's first law, I believe by now you know how to state Newton's first law in weights. So Newton's first law in weights states that an object will remain in its state of rest or motion at a constant velocity unless a non-zero resultant force acts on it, or a non-zero net force acts on it, right? So an object will remain in its state of rest or motion at a constant velocity unless a non-zero net force or a non-zero resultant force acts on it, right? So that is Newton's first law. So if an object is at rest or stationary, so it's rest or stationary or constant velocity, right? So that is Newton's first law, or application of Newton's first law. Here we can also add forces at equilibrium. So here, what is that we know is that the net force acting on that object, if an object is at rest or is stationary or is moving at a constant velocity, not constant force, but constant velocity or constant speed, right? Or if the forces are at equilibrium, F net is equals to 0 newtons. And if F net is equals to 0 newtons, right, it means that even the acceleration is 0 meters per second squared. Okay, so that is application of Newton's first law. So when you read the statement, and then the statement says an object is at rest, or an object is stationary, or an object is moving at a constant speed or constant velocity, or forces acting on an object that are at equilibrium, so you should know that that is application of Newton's first law, right? And if it's application of Newton's first law, it means that the net force, we are not saying that not forces acting on that object, but the sum of the forces acting on that object is equal to 0 newtons. And if the sum of the forces acting on that object is equal to 0 newtons, it means that even the acceleration of that object or of that system is 0 meters per second squared. Okay, so that is application of Newton's first law, right? Then Newton's second law, right? So in weights, according to our exam guidelines, right? So in weights, when a net force acts on an object an object will accelerate in the direction of the net force or of the force with an acceleration that is directly proportional to what? To the force, and inversely proportional to what? To the mass of an object. So when it comes to Newton's second law, an object is accelerating. And if an object is accelerating, the net force acting on that object is equals to what? Ma. Okay? So net force equals to what? Ma. It means that here the net force here is unequals to 0 newtons when it comes to Newton's second law. The object is accelerating. All right? So then when it comes to Newton's third law, right? Newton's third law states that when body A or when object A, right, exerts a force on object B simultaneously exert an oppositely directed force of equal magnitude on what? On object A. So that is Newton's third law, right? So here, now I can give you an example here. We are having two objects, maybe object A, which is in contact with what? With object B. So what are they saying here? When object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude of what? On what? On object A. So force A on what? On B will be equals to negative force B on what? On A. Why am I saying negative? Right? They're saying object B will simultaneously exert an oppositely directed force of equal what? Magnitude on what? On object what? A. Oppositely directed force. So which means that that force acts in the opposite what? Direction. All right? Then another thing which is important here with Newton's third law is that although these two forces are equal in magnitude, acting in opposite directions, but they are not exerted on the same object. So here, if we say FA on B, so that force is on object B, right? And then FB on A, so that force is on object what? A. So those two forces, they are not exerted on the same object, right? So this, if this is object A, right? Then we are saying here FA, so this is object A, and then this is object B. So we are saying FA on B, so it's on B, right? So this force is acting in this direction. So this is force A on what? On B. Then force B on A. This is force B on what? On A. Force B on what? On A. So you can see if this one is 4 newtons, this one is also going to be what? 4 newtons. So this one is 4 newtons to the left, the other one will be 4 newtons to which direction? To the right. So they are equal in magnitude, acting in opposite what? Directions, but they're not exerted on what? On the same object. Then Newton's third law, again, you can also talk about action-reaction pairs or action-reaction pair of forces. So we'll talk about that. There's a question which will address that, all right? Then when it comes to Newton's law of universal gravitation, right? So every particle in the universe attracts every other particle with a force or a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers, right? So in symbols, right, you have F equals to G m1 m2 over what? Over r squared, where F is the gravitational force in newtons, G is the gravitational constant, which is 6.67 times 10 to the power negative 11. Then m1, that is the mass of object 1 in kilograms. M2, that is the mass of object 2 in kilograms. Then r, that is the distance between the centers of those two objects, which is measured in what? In meters. All right. So in that case, please let us make sure that if the equation is application of Newton's law of universal gravitation, let's not forget that m there should be in what? In kilograms. So if you're given m in grams, then you need to convert those grams to kilograms. But when it comes to paper 2, right, when it comes to stoichiometric calculations, that that mass should be in what? In grams. But when it comes to paper 1, the mass it's in kilograms, right? Then what is r? That is the distance between their centers. So from the center of object A to the center of what? Of object B, and that distance should be in what? In meters. And again, learners, let's not forget a square when it comes to what? Substitution, right? So F here is directly proportional to the product of the masses, right? Which means that the relationship between F and the product of the masses, right, it is directly what? Proportional, right? Then F is inversely proportional to the square of the distance between their centers. What is the relationship between F and 1 over R squared? Is directly what? Proportional. But what about F? What about F and what? And R squared or R? The relationship will be inversely what? Proportional. So these are some of the things that you need to look at when we are busy with what? With the multiple choice what questions. So some questions, you know, they will come from what we have just done here. Okay, so when a spaceship moves at a constant, so immediately when they mention constant velocity, which law is that? Which application is that? Or is the application of which law? It should be what? Newton's first law. All right. So when a spaceship moves at a constant velocity, it means that the resultant force acting on the body is zero. That is true. The resultant force, not just a force, but the resultant force, the sum of the forces acting on that object should be equal to what? Zero. So we can even add here is not only the constant velocity. It can also be an object being at rest, or an object that is stationary object, or forces that are at equilibrium, or forces acting on an object are at what? Equilibrium. So net force acting on that object will be equal to 0 newtons. Acceleration is also going to be 0 meters per second squared. If an object is stationary, moving at a constant speed or constant velocity, forces are at what? Equilibrium, right? So the law that is going to explain that here, it is going to be what? Newton what? First law. But when an object is accelerating, then obvious it's going to be what? A Newton's second law of motion. Then when it comes to action-reaction pair of forces, then that will be Newton's third law, right? Then the relationship between the gravitational force and the product of the masses, or the distance, or the square distance between their centers, then that will be Newton's law of universal what? Gravitation. All right. Then let's look at 1.3. So you saw that 1.1, it was on different kinds of forces. So when it comes to different kinds of forces, right? So you need to categorize those forces as being contact and non-contact, and give examples of contact, non-contact, and then also the definitions are very, very important. Okay, then so that you'll be able to answer such questions. Then when it comes to 1.2, it was application, or it was Newton's first law. Then let's look at this one and see its application of which law. All right, so here we are having a sphere. So this is a sphere, right? So a sphere is attached to a string. So this is a string. Okay, this is a sphere, right, which is suspended from a fixed horizontal bar. So this is a bar. All right, so this is a bar. The reaction force to the weight of the sphere, as described by Newton's third law, is, so here you can see its application of what? Of Newton's third law, right? Action-reaction pair of what? Of forces. All right, so when it comes to action-reaction pair of what? Of forces, right? When I look at this diagram, there's a lot that we can talk about. Okay, there are so many pair of forces that we can talk about here. So if our focus is the sphere, right? So you can see that the sphere is attached to what? To a string. So there's contact between what? The string and what? And the sphere. So if there is contact here, obviously there will be an application of Newton's third law. So there will be a force exerted by what? By the sphere on what? On, so let me just use S for the sphere. Sphere on what? On the string. Oh, string. Right? So there's a force exerted by the sphere on the string, and then which goes together with what? The force exerted by what? The string. So force exerted by the string on what? On the sphere. So this is action-reaction pair of forces, right? Then the focus here is the sphere, right? So the sphere is in contact with what? With the string. So there's a force exerted by the sphere on the string, which goes together with the force exerted by the string of what? On what? On the sphere. So that is those are action-reaction pair of forces, right? Then remember, if we can draw a free body diagram for a sphere here, right? So for a sphere, if frictional force or air resistance is ignored, then if this is a sphere, then there will be tension, all right? So there will be tension. So there's T there. And also what? The gravitational force, right? So those are the two forces acting on the sphere, right? So there's tension because of that string connected to the sphere, and then there will be what? The gravitational what? Force, right? So another reaction pair of what? Of forces, right? So there's a force exerted by what? By the Earth on what? On the sphere. And it goes together with what? The force exerted by what? By the sphere on Earth. Or you can say the force exerted by weight, right? Remember, because weight, that is the gravitational force exerted by the Earth on objects on or near its what? Surface. So instead of using the word Earth, you can use what? Weight, right? So force weight on the sphere, and then force sphere on what? On Earth or what? Or weight. Right. So these are a pair of forces for the sphere, right? So the focus is the sphere, right? If the focus was the string, you can see that the string is in contact with the sphere, right? So there will be a force exerted by the string on the sphere, which goes together with what? The force exerted by the sphere on the string, right? The string is also in contact with the horizontal bar, right? So there's a force exerted by the string on what? On the bar. The force exerted by the bar on what? On the string, right? Then remember, weight or gravitational force is a non-contact force, right? So, and weight is always there, right? Or gravitational force is always there. Whether an object is hanged, it's in motion, you know, so gravitational force is always there, all right? So there's the force exerted by the string on Earth. There's a force exerted by the Earth on what? On the string. Or the force exerted by the weight on the string, the force exerted by the string on what? On the weight. But here, the focus is the sphere. So these are the two, you know, action-reaction pair of forces here, all right? Force string or force a sphere on the string, force string on what? On the sphere. Force weight on the sphere, force sphere on what? On the weight or the Earth, right? So the question, let's look at the question. The reaction force to the weight of the sphere, as described by Newton's third law, is, remember the focus here, they're saying the reaction force to the weight of the sphere. So the focus here is weight and the sphere. So the focus is here. Force weight on the sphere, force sphere on what? On the weight. So it's one of those two forces, right? So it's weight and the sphere, all right? So it's not the sphere and the string, the sphere and the bar, right? So the focus is weight, which is Earth. It can be Earth and what? And the sphere. Let's look at option A. The force of bar on the sphere. So the focus here is the bar and the sphere, but our focus should be what? Earth and the sphere. So this is out. Second one, the force of the string on the sphere. The focus is not the string, right? And the sphere, but the focus is Earth and what? And the sphere. So this is also out, right? C, the force of the sphere on Earth, right? So sphere on Earth, that is our focus, right? So I'm looking at D, the force of bar on the string. So we are not focusing on the bar, we are not focusing on what on the string, we are focusing on the sphere and the Earth. So the correct answer here will be what? Will be C. So they're saying the reaction force to the weight of the sphere, the reaction force to the weight, right? So actually the force that is given to us here is force weight on the sphere. That is the force that is given to us. Ne? So the force weight on the sphere, because they're saying the reaction force to the weight of the sphere, right? To the weight of what? Of the sphere. So here we're given what? Force weight on the sphere. And then the reaction force would be what? Force sphere on what? On weight, right? Or Earth. Force sphere on weight or what? Or Earth. So the correct answer there will be what? Will be C. So that is application of Newton's what? Third law. Let's look at 1.4. A net force, right? F, which acts on a body of mass M, causes an acceleration A, right? So when I read the statement, I can tell which law is this, right? The law is Newton's law of it's what is Newton's second law, all right? Because the object here is what is accelerating, okay? So a net force F, which acts on the body of mass M, causes an acceleration of A. If the same net force F is applied to a body of mass 4m, the acceleration of the body will be, okay, the original acceleration, because the focus here is the acceleration. We know that net force, this is application of Newton's second law, F net is equals to what? Ma, right? What is our net force? Is F, right? What is our mass? We are told it's what? So our net force is F, our mass is M, right? Our acceleration is what? Is A. So we are having F equals to what? Ma. So this is the, okay, then what is the original acceleration? I'm making A the subject of the formula, right? I'm making A the subject of the formula. So A will be what? F over what? Over M, right? So this is the original acceleration, this one. So this is the original what? Acceleration. Then, if there's the same net force, if the same what? Net force is applied to a body of mass 4m, the acceleration of the body will be, right? So the mass now, so we are having the same F, right? F is the same. Then the mass is still the mass now is not m. The mass is what? Is 4 what? 4m, right? What are we looking for? We are looking for what? Acceleration. So I'm making A here the subject of the formula. So A equals to F over 4 what? 4m. This is new A now. So A new is F over 4m, which is the same as 1 over 4 F over m. Okay? I hope we are still together, right? Then what is F over m? F over m is the same as original what? A. So where there is F over m, I can substitute by what? By A. So the correct answer here will be what? Will be B. Okay? So our original A is equals to F over m. The mass now is increased to 4m, right? So there is original F, which is still F, equals to now m is 4 times larger, right? So it's 4m times what? Times, I'm looking for what here? For A. So I'm making A the subject of the formula, the new A now. So the new A will be what? F over 4m, which is the same as 1 over 4 F over m. And what is F over m? This is equals to original what? A. So which means that new A new, right? When the mass is increased to 4, A nu will be what? 1 over 4a. So the correct answer there will be what? Will be B. Okay? Right. This is Newton's law of universal gravitation. Object X exerts a gravitational force F on object Y, right? When the distance between the centers of the object is what? Is R. So object X exerts a gravitational force of F on object what? Y. When the distance between the centers of the object is what? Is R. So original F is G M what? Mx My over what? Over R squared. Right? So you're having mass of X, mass of Y, and the distance is what? Is R. So where there's distance, I will substitute by what? By R. So this is original F. Then F nu. The distance R is now halved. The distance R is now what? Halved. Which one of the following represents the gravitational force of X that X exerts on what? On Y. So now the distance is what? Is halved. So now for F nu I'm having what? G M is of X is still M, and then M of Y is still M of Y, over the distance is now what? Halved, right? So the distance before was R, but now is half R. Now is half what? R. Then let's not forget a square, because there's a square when it comes to that what? Equation. So this is the same as G mx my over 1 over 2 squared is 1 over 4 R what? R squared. Okay? Then this is the same as 1 over 1 over 4, right? What is this? What is Gmx my over R squared? Gmx my over R squared is the same as this one, is F original. Ne? So this is F what? Original. And of F original, remember, is what? Is F. Okay? So this is the same as, so this Gmx my over R squared is F. So hence here I've substituted by what? By F. Where am I getting that from? From here. F is Gmx my over R squared. What about new F? Is Gmx my over half R, because the distance is now halved, but all squared, which is going to be Gmx my over 1 over 4 R squared. Then what is Gmx my over R squared? This is equivalent to what? To F original, which is just F. Ne? So I'm having 1 over 1 times 4 over 1 F, ne? Which is the same as what? So F nu will be 4 what? 4F. So F nu will be what? 4F. So the correct answer there will be what? Will be D. Okay? Let's move to 1.6. Two small identical metal spheres, each carrying equal charges of Q, are brought into contact and then separated. The charge on each sphere will be now, so this is electrostatics, all right? So we are having two charges, right? So we have charge maybe A and then charge B, and then what is the charge on each is Q, right? Then they were brought into contact. You know, immediately when they say they are brought into contact, what must come to your mind, right? During contact, ne, electrons will be transferred until these two spheres, they have equal what? Charge. Then they will what? They will repel. Ne? Then the charge on each sphere, if objects are brought into contact, ne, it's given by Q nu. Charge on each sphere after contact will be Q1 plus what? Q2 over what? Over 2. Okay? So Q1 is Q, Q2 is also what? Q, over what? Over 2. This is the same as what? 2Q over what? Over 2, which is the same as what? As Q, because 2 over 2 is 1, and 1 times 2 is what? Is Q. So the correct answer here will be what? Will be C. So immediately when they say charges were brought into contact and separated, during contact, electrons are transferred from a sphere with excess electrons to a sphere with the shortage of what? Of electrons. Until these two spheres, they have what? The same charge, then they will repel. And they will repel. After repelling, they will have what? The same charge. And how do we calculate that same charge? How do we calculate that new charge on each sphere? Is Q1 plus Q2 over what? Over 2. Then we'll get a charge on each what? Sphere after what? They were brought into what? Into contact. Ne? Right, let's move to 1.7. So 1.7, a circular coil. So it's Faraday's what? It's electromagnetism, this one. All right. So a circular coil is placed inside a magnetic field and rotated clockwise to induce an EMF, right? So to induce what? An EMF. Remember, EMF is induced across the ends of a conductor if there is relative movement or motion between the coil and what? And the magnetic field. As long as there's that relative motion, relative movement between the coil or between the conductor and the magnetic field, EMF will be induced across the ends of that conductor. So that is electromagnetism, right? Or that is Faraday's what? Faraday's law, right? Yes. Then which one of the following changes will increase the induced EMF? But how is it being induced? Remember, that is electromagnetic induction, right? How do we induce EMF across the ends of the conductor, right? So how do we induce EMF? EMF is induced across the ends of the conductor if there is relative movement or motion between the conductor or the coil and what? And the magnetic field. As long as there's that relative motion between the two, which is the coil and what? And the magnetic field, EMF is what? Is induced across the ends of what? Of that conductor. Then after the EMF is being induced, how can we now increase the amount of EMF that is induced across the ends of that conductor? There are certain things that you can do. One, I hope we are all aware. You can increase the number of windings or turns in a coil, right? You can use a stronger magnet to increase the strength of the magnetic field, okay? You can increase the speed of rotation of the coil, right? So increase the speed of rotation of the coil. If it is the coil that is moving, then we can increase the speed of rotation of what? Of the coil, right? Or if it is the magnetic field that is moving, for example, if you are given a solenoid and the magnet, so if you move the magnet in and out of the coil faster, right, the EMF that is induced across the ends of that solenoid, it is going to do what? To increase, right? So to increase the amount of EMF induced in a coil, we can increase the number of turns or windings in the coil. You can use a stronger magnet to increase the strength of the magnetic field. You can also increase the speed of rotation or move the magnet, the magnet in and out of the coil faster. So by doing that, you will be increasing actually the amount of EMF that is induced in what? In that coil, right? But how do we induce the EMF in a coil? Electromagnetic what? Induction, right? As long as there's that relative motion between the coil and the magnetic field, EMF is what is induced across the ends of that conductor. And how can we increase the amount of EMF that is induced? We can increase the number of turns or windings in the coil, increase the strength of the magnetic field by using a stronger magnet, increase the speed of rotation of the coil, or move the magnet in and out of the coil faster. Then by doing that, you will be increasing the amount of EMF that is induced in what? In a coil, right? So let's look at this one. Which one of the following changes will increase the induced what? EMF. The EMF is already induced, okay? But now what is that we want to do? We want to increase the amount of EMF that is induced in that coil, rotating the coils slower. So if we rotate the coil slower, what is going to happen? The amount of EMF that is induced is going to be it's going to decrease, or it's going to be less, right? Unless if we are rotating that coil faster, then the amount of EMF induced will increase. Remember, what is it that we want to do here? We want to increase the amount of EMF that is induced in what? In a coil. So if you are going to move or to rotate the coil slower, then the EMF that is induced in that coil is going to do what? To decrease, right? So this is out because we don't want to decrease the amount of EMF. We want to increase the amount of EMF, unless if this option was saying rotating the coil faster, then we're going to check that option. But they're saying rotating the coil slower. That one will decrease the amount of EMF that is induced in a coil. Right, so let's look at B. Increase the number of turns or windings of the coil. So if you increase the number of turns or windings of a coil, then the EMF that is induced in that coil is going to do what? To increase. So the option B is correct. Decreasing the strength of the magnetic field by using a weaker magnet. If we use a weaker magnet, the amount of EMF that is induced in that coil is going to be what? Less, or it's going to decrease. So we can't decrease the strength of the magnetic field if we want to increase the amount of EMF that is induced in that coil. So this is out also. Changing the polarity of the magnets has nothing to do with the amount of the EMF that is induced in that coil. Whether you change the polarity from north to south, from south to north, that has nothing to do with the amount of the EMF that is induced in what? In that coil. So this is also out. Okay, so the correct answer there, learners, will be what? Will be B. Right. Now 1.8. 1.8 is electric circuits, right? 3 identical light bulbs. So these bulbs are identical, right? So they have the same resistance. So if the resistance of X is 2 ohms, Y is also going to be 2 ohms, Z is also going to be 2 ohms. Power dissipated by each of those light bulbs, if for X is 2 watts, for Y is going to be 2 watts, even for Z is going to be what? 2 watts. So they're saying they're identical. So they have the same resistance. Power dissipated by each should be should be equal. So it's like, for example, you are using a 60 watts light bulb or a 100 watts light bulb. Ne? Right. So let's look at this question. So 3 identical light bulbs, X, Y, and Z, are connected in a circuit diagram as shown below. So the internal resistance of the battery is negligible when switch S is closed. So the reading on the ammeter A1. So there are 3 ammeters here. There's A1, A2, and A3. So the reading on the ammeter A1 is 2.5 amperes, right? So for now, the switch is open. Let's start there. So if the switch is open, right, so you can see where the switch is located. There's only one path for current to do what? To flow. So if the switch is open, it means that there will be no flow of what? Of current. Unless if the switch maybe was here, was somewhere here, and it was open. This part, no current was going to pass through, but this part, because these 2 bulbs are connected in parallel, then it was going to be able to pass through, right? But the way it is connected, then it shows that there is only one path for current to flow where it is located. Then if it's open, the reading on A1 would be 0 amperes, the reading on A2 would be 0 amperes, the reading on A3 would be what? 0 watt amperes, right? If it is open, I hope it's clear. And if the reading on A1 is 0, even the potential difference here will be 0 volts. Potential difference here will be 0 volts. Potential difference here will be what? 0 volts. Why 0? R is given by V over what? Over I, right? Then I'm looking for V. V is equal to IR. Then if my I is 0, then my V is also going to be what? To be 0. If the switch is open, you can see there's no flow of what? Of current. There's only one, where it is located, there's only one path for current to do what? To flow. Okay. Right? Now the switch is closed. Now the current is flowing. Then what is the reading on A1? The reading on A1 is 2.5. What will be the reading on what? On A2. So let's trace the current here. Current moves from positive terminal to negative what? Terminal. So this is how it's going to flow, right? So when it comes to this A1, current is flowing as 1, right? It's a unit, right? Which means that this A1 matches what? The total current of what? Of the circuit. So the total current of the circuit is 2.5 amperes. Then let's trace again. you can see X is connected in what? In series. So the current that will pass through X is going to be what? 2.5 amperes. Is the total current of what? Of the circuit. But when it comes to this point now, there's a split. And the current is going to split equally. Why equally? Because Y and Z and actually the focus is, let's look at Y and Z. Y and Z, they're identical. The resistance of Y is equal to the resistance of what? Of Z. Okay? So obvious the current will be divided equally, right? So what is 2.5 divided by 2? 2.5 divided by 2, it's 1.25. So here it's going to be 1.25 amperes, the reading on A2, 1.25 amperes, the reading on what? On A3. Okay? Right. So I hope you understand what we are doing here. Why the current is divided equally is because Y and Z are identical. Unless if the resistance of Y was greater than the resistance of, let me do that, resistance of Y, let's say it was greater than the resistance of Z. Ne? R is given by V over I. Okay? And when the resistors or the bulbs are connected in parallel, what remains the same is the potential what? Difference. Ne? So, I is given by V over what? Over R. Ne? So, at constant V, I is inversely proportional to what? To R. Which means that the resistor with high resistance will have what? Low current that will pass through it. A resistor with what? With low resistance will have what? A greater current that will pass through it. Ne? But in this case, the resistors or the bulbs are what? Identical. So which means that the current will be divided equally. Okay. Right. Then now let's look at the question. Okay. The question. Which one of the options, sorry about that, which one of the options correctly describes the reading on the ammeters in ampere if light bulb Z burns out? Let's check where is Z. So this burns out. So if Z burns out, the current will still flow. The current will still flow through Y, even through X. So it burns out. So can you see that we are removing a bulb that is connected in parallel? Remember, the more we connect the bulbs in parallel, the total resistance of the circuit decreases, right? So if we remove, or if the bulb that is connected in parallel burns out or is being removed, what will happen to the total resistance of the circuit? The total resistance of the circuit will what? Will increase. Let me just give you an example. Let's say what is this? The resistance of each bulb was 2 ohms, 2 ohms, 2 ohms, right? Okay? So, if these two are connected in parallel, what will be the effective? What would be their effective resistance? It will be 1 over 2 plus 1 over 2, right? Remember, it will be 1 over R P equals to 1 over R1 plus 1 over what? Over R2 equals to 1 over 2 plus 1 over 2. Ne? So 1 over 2 plus 1 over 2, right, is going to be what? 2 over 2, right? Which is equals to what? Which is equals to 1. So the total will be what? Will be 1, right? But now, remember the total, the effective resistance for parallel connection is going to be 1, right? If that Z is still there, connected in parallel to Y, right? So now if it burns out, the only thing now that you are left with is going to be this Y and this X. And now this X and this Y, they are connected in what now? In series. And how are we going to calculate their total? The total will be 2 plus 2, which is equals to what? 4. But the total before was 2 plus 1, which was equals to what? 3. When that Z was still there, connected in parallel to Y. So it was 3 R total before, it was 3 ohms. Then now R total after Z bends out is going to be what? 4. Can you see that if we are removing removing a bulb connected in parallel, what happens to the total resistance of the circuit? It increases. So the total resistance of the circuit will increase when that resistor which is connected in parallel is being removed or it bends out, or when that bulb that is connected in parallel bends out. So what is going to happen to the total resistance is going to increase. So R total is going to do what? It's going to increase. And if R total increases, right, what about I total, total current of the circuit? Total current of the circuit is going to decrease. Why am I saying it's going to decrease? I'm not getting that from heaven, right? But this is coming from the equation R equals to V over what? Over I. What is this R that I'm talking about? Is the total resistance. What is this V? Is the total potential difference, which is equals to the EMF of the battery. Okay, the EMF of the battery remains the same. That is the total potential difference there, all right, over the total what? Current. So at constant EMF, because we are not changing the number of cells, right, there is still 2 cells. So which means that the EMF is still what? The same. So at constant EMF, right, if R at constant EMF, if R total, we said R total will increase. Right? If R total increases, what about I total? I total will what? Will decrease. Hence I said the I total will what? Will decrease. What was our I total before? It was 2.5. So there will be a decrease there. All right? So it should be what now? Less than what? 2.5. So I don't care about which value, but the value should be less than what? 2.5. So here it should be less than 2.5. Even here, you must have what? The same value. If I'm saying it's less than 2.5, let's say it's what? 1.8 amperes. I'm just giving you an example. Because it should be less than 2.5. I hope you understand why I'm saying it should be less than 2.5. It should be less than 2.5 because we are removing a bulb connected in what? In parallel, which increases the total resistance of what? Of the circuit. And if total resistance of the circuit will increases, what will happen to the total current of the circuit? It will decrease at constant EMF. All right? So if it decreases, obviously it should be less than 1.8. But remember, the current that was passing through X, it was 2.5. Now will be 1.8 amperes. And this X and this Y, they're connected in what? In series. Series bulbs, they don't divide current, they divide the potential what? Difference. Which means that even the current that will pass through Y is still going to be 1.8 amperes. So the current that should pass through X and Y should be the same and less than what? 2.5. Then what will be the current that will pass through X? 0. Why? Because that X, that Z bends out. It's no longer there. So what will be the reading on A3? It's going to be what? 0 amperes. Reading on A3 is 0 because Z bends out. Reading on A1 and A2 should be equal. Why equal? Because now our X and Y, they are connected in what? In series. And series connection, in series connection, we all are aware of that from grade 10. In series connection, current is the same throughout, irregardless of their resistances. So current is the same. What is being divided, it is the potential what? Difference. So the current that will pass through X should be equal to the current that will pass through Y after Z has bent out, right? Then, and that current should be less than 2.5. But in A3, the current should be 0. So let's check where the current is 0 for A3. The 0, 0, 0. This, it can't be, right? Then, look at A. Current in A1 and A2 should be equal. I agree. But yes, as long as you can see it's equal, but it shouldn't be greater than 2.5. It should be less than what? 2.5. Yes, it should be equal, but it should be less than 2.5. Look at B. B, they're saying it's 2.5, 1.25. We are expecting the current in A and A2, A1 and A2 to be equal and less than 2.5. So then this is out, right? Look at D, right? It's 1.2, 1.1. We are expecting it to be equal. This is out, right? Then let's look at C. It should be less than 2.5 and it should be equal. A1 should be equal to A2. You can see that. So the correct answer here will be what? Will be C. So you analyze the circuit, learners, right? Understand what is going on there so that you'll be able to answer what? The question. So when it comes to electric circuits, you should know the basics, because if you don't know the basics, then you'll struggle to answer what? The question. So these are the solutions, and you can see the time that we took to do those multiple choice questions. But during an exam, you cannot do that. At least spend 20 minutes when it comes to your section A, not more than that, because you won't be able to do other structured what questions. So please don't spend a lot of time when it comes to multiple choice questions, but you should give multiple choice questions enough time. All right, because if you can lose that 20 marks, it means that you are writing out of 130, and then we are not even guaranteed that we are going to get that 130 marks, right? So you can't leave out section A, you can't leave out the multiple choice what questions. And when you answer multiple choice questions, answer them with understanding. Don't just say the answer is A, is B, I've never seen B in my options, then let me choose B. You cannot do that. So you should understand, the concepts for you, all the physics concepts for you to be able to answer the multiple choice questions. So they're not actually separated from what you have learned when it comes to all these knowledge what areas. So understand all the concepts, then you will be able to answer the multiple choice questions. Now let's move to the structured questions. So this is Newton's laws and application. Again, learners, read with understanding. You are also given a diagram. So the diagram will assist you to understand the statement better. That is the nicest thing about physical sciences. We are not just given a statement. There's a statement which is accompanied by what? By the diagram, all right? So then you shouldn't struggle to understand the statement, and you shouldn't struggle to understand the questions that are being asked, right? So Newton's law and application, Newton's laws and application, but which law? Because there are 4. You will get that from the statement, okay? A 8-kilogram block on a rough horizontal surface. A physics learner cannot just pass, right? They are saying rough, which means that here there is frictional force. What type of friction? But what is frictional force? A force that opposes the motion of an object. It acts parallel to what? To the surface. What type of frictional force? If the object is at rest, that is static. If it's about to move, that is maximum static. If it's in motion, that is kinetic friction, right? It's connected to a 2-kilogram block by a light inextensible string passing over a frictionless pulley, as shown below. The 8-kilogram block moves at a constant speed. Moves at what? At a constant what? Speed. So you need to underline that. When pulled by 29.6 newtons horizontal force to what? To the right. This is the force that they're talking about. The frictional force acting on the 8-kilogram block is 10. But this system is moving at a constant what? Velocity when it is pulled by a force of 29.6 newtons to which direction? To the right. So which law is this, right? It's application of which law? Newton's first law, because an object is moving at a constant what? Speed when it is pulled with a force of 29.6 newtons horizontal force to which direction? To the right. Ne? So we have 2 objects. It's the 2-kilogram object which is hanged vertically, and then the 2 objects that are connected by a light inextensible string. So obviously there's a string there, which means that there should be what? Tension force. And then there's a force that is applied to that 8-kilogram block, which causes an object, the whole system, to move to the right at a constant speed. Okay. Then, first question, state Newton's second law of motion in weights for 2 marks. When a net force acts on an object will accelerate in the direction of the force with an acceleration that is directly proportional to the force and inversely proportional to the mass of what? Of an object. So you can't lose marks when it comes to that. So draw a labeled free body diagram for the 8 kilogram block. You can see it's 5 marks there. So if it's 5 marks, this is a skill. It means that we're expecting how many forces? 5 forces, not the components. Don't count the components as what? As forces. So you're expecting what? Forces. If a force is applied at an angle, we don't count F, Y, and Fx as 1. F, Y, and Fx is 1 mark. They represent F, right? When it comes to an inclined plane, components of weight, your Fg parallel and Fg perpendicular, we don't count those ones as one force. No, both of them, they will give you how many marks? One mark. Ne? Then again, you are advised, or you are encouraged that when you draw a free body diagram, you don't include the components. If an object is on an inclined plane, do not include the components of weight. Ne? If an object is pulled maybe horizontally at a force that is at an angle, right? So don't draw the components of that force, your Fx and Fy, right? So encourage, please, we are discouraging you from doing that at grade 11s. So you draw what you see, okay? So if a force is applied at an angle, we want to see that force, not the components of that force. But remember again, you will need those components for your calculations. Same when it comes to an inclined plane. You will draw your Fg, your weight, acting downwards, but when it comes to calculations, you need those components of weight, your Fg parallel, and your Fg what? Perpendicular. So, but you are advised not to include the components when you're drawing a free body diagram, components of weights on an inclined plane, or components of a force if a force is applied at what? At an angle that is greater than 0 degrees. Okay. Then, so we are expecting how many forces here? 5 forces. So a free body diagram represents an object by a dot. So there's that force which is always there. So immediately when they say draw a free body diagram indicating all the forces, already I know 1 mark is there, because whether the object is on the horizontal plane, vertical plane, inclined plane, Fg is always there. So it's where I have to start. So I'm having my Fg there, already I'm having a mark. Remember, a mark is given to a force and the label, together with the label, right? A correct label, right? So it's not given to an arrow. It's not given to, you know, this line without an arrow. So it's a line with an arrow plus the label, and that force should start from the dot, not from the atmosphere, for example, right? It should start from what? From the dot. You can see my force is starting from the dot. It's not something like this. So this is wrong. Even if you can label, it's wrong because it's not starting from what? From the dot. So please make sure that you draw correct forces starting from what? From the dot. Okay. So I'm having my Fg, and this object is on the surface. So there's a force exerted by the surface on an object which is in contact with, and that force should be what? The normal force. So it's N, or we can accept Fn, right? Then is Fg or weight, okay? But the correct label for normal force is capital letter N. We do accept Fn, but the correct one, as per the exam guide or the ATP, it should be what? N, right? So already now I'm having 2 marks. I'm also having a force that is applied to the right, which is F, or 29.6 newtons. There is another mark there. Okay, there is tension. You can see that. So there's tension. T is for tension, but we do accept Ft. But the correct label or the correct symbol, let me put it like that, for tension is T, capital letter T, not small letter t, because small letter t, that is time, right? Then for the normal force, correct symbol is capital letter N, not small letter n, because the small letter n is for number of moles, right? Or for number of electrons. So please be careful when it comes to that. So already I'm having how many marks now? 4. Then it's on the rough horizontal surface. So there's friction which will oppose the motion of what? Of an object. So what type of friction? I can write F here, right? Or Fk, because an object is in motion. So it's moving to the right after that 29.6 newtons is being applied. It's moving to the right at a constant what? Velocity. So how many forces am I having now? It's 5, right? So which is out of how many marks? 5 marks. Yeah? Then, now they want us to calculate. Calculate the tension in the string, right? Calculate the tension in what? In the string. So if they want us to calculate the tension in the string, okay, I can either, there's tension, so let me draw the forces here. So the forces here, there's tension for the 2 kilogram block. There is also Fg there. So this tension here should be equal to this tension, right? So if I want to use object, the 8 kilogram object, I need F. Yes, I do have F. I need tension. I need Fk, right? Am I given Fk? Yes. Okay. So I'm giving Fk. Fk, frictional force acting on the 8 kilogram block is 10. I'm giving what? Fk. I'm giving F. I'm looking for what? For Fk. So one of the things that I can do here for this question, that's the reason why it's 3 marks, can say F net is where we have to start, equals to what? Ma, right? F net is the sum of the forces. Which forces? Horizontal what? Forces. And please make sure that you also take into consideration the issue of direction there. So those forces that are not acting in the same what? Direction. So which direction are you taking as positive? In most cases, learners, we always take the direction of motion of an object as positive. So in this case, what is the direction of motion of an object? Is to the right. Ne? So we are taking right as what? As positive. So if you are taking right as positive, remember the focus is these forces. Is 29, is it 29? Let's double check that. So 20, yes, it's 29.6 newtons, which is our F. I'm also having what? The tension. I'm also having what? The frictional force, which is equals to what? 10 newtons. Ne? That is my focus there. Okay? So I'm taking it right as positive. So it's F minus what? T minus what? Fk equals to what? 0. Why is it equals to 0? An object is moving at a constant what? Velocity. So acceleration is also going to be what? 0. And then therefore F net will be 0. So F is 29.6 minus T minus 10 equals to 0. So minus, what I can do here, I'm having 29.6 minus 10 equals to T. I'm transposing T. You can see my T there is negative. Ne? So what is 29.6 minus, is 29.6 minus what? Minus 10. So I'm getting 19.6. So tension is going to be what? 19.6 what? Newtons. So that is the tension. Okay? Or I can use object what? Object, I can use object, the 2 kilogram object, the one that is hanged. So again here, I'm having F net equals to what? Ma is where I have to start because marks are for the equation. Marks are not for F net equals to 0. Why are you saying F net is equals to 0? It's because acceleration is what? Is 0. The object is moving at a constant what? Velocity. So the velocity is not changing. So if the velocity is not changing, remember acceleration is the rate of change of what? Of velocity. So if the velocity is not changing, acceleration is going to be what? 0. Right. So then F net here, it is going to be what? Which direction do you take as positive? Is to the right. So which means that here, this is how the system is going to move. Right. So tension here is going to be positive. Then minus mg, which is your Fg, equals to what? 0. Tension minus 2 times what? 9.8 equals to 0. Then tension is going to be what? What is 2 times 9.8? 9.8 is going to be what? 19.6. So it's 19.6 what? Newtons. So 19.6 what? Newtons. Whether I'm using object, the 2 kilogram object, the 8 kilogram object, the tension is still 19.6. So remember, if tension is 19.6 here, even for the 8 kilogram block, the tension is going to be what? 19.6. So we got 19.6 for the tension. 4.4. 4.4. Apply Newton's second law to each block and calculate the magnitude of the acceleration of the 8 kilogram block. So now we are moving from Newton first, right? So for 4.3, we're using Newton, application of Newton's first law. Then 4.4, now the focus is Newton's second law, right? They want the magnitude of the acceleration of the 8 kilogram block. Now they've increased the 29.6 to 50. That is why the object now is accelerating. At 29.6 newtons, it was moving at a constant velocity. Then that 29.6 was increased to 50 newtons. Then the object is now accelerating. Then they want us to calculate the magnitude of that acceleration. Now, maybe before that, another thing which is very, very important here, they are saying calculate the tension. They didn't say calculate the magnitude of the tension. And what we know, tension is a force. Force is a vector. It has both magnitude and what? And direction. So you need to be careful again, learners, on how they ask questions, right? They're saying calculate tension. They didn't say calculate the magnitude of the tension. If they just wanted the magnitude of the tension, this is correct. We are done, right? But they are also looking for what is the direction. So here is tension is 19.6 newtons. In which direction? From the free body diagram to what? To the left, right? Calculate the tension in what? In the string. So it's to the left if we are using which block, 8 kilogram block. Then if we are using the 2 kilogram block, the tension is acting in which direction? Upwards. So it's going to be up. So it will depend on which object did you use, right, to get that tension. Unless if they wanted us to calculate the magnitude, then it's just 19.6 newtons. But it's tension, which is a force, a vector, both magnitude and what and direction must be shown. Okay, then apply Newton's second law to get the magnitude of the acceleration of the 8 kilogram block. So Newton first law, so the forces, the only thing that is going to change here, because I think it's what they've changed, is what is going to change here is this 29 to what? To 50 what now? 50 newtons, right? Okay, so I'm using which object? This object. Now I'm having 50 here. I'm having tension. Tension. I'm having what? Frictional what? Frictional force. I'm having frictional force, right? So F net equals to MA. So F net is 50 minus T minus FK minus FK equals to 8 times what? Times A, right? Which is 50 minus T minus FK, they said is 10, equals to what? 8A, right? Which is going to be what? 40 minus T equals to what? 8A. That is equation what? Equation 1. Okay. Then, for object, 2 kilogram object is FG here and what? And tension. So it's F net equals to MA, which is T minus mg equals to ma. So T minus what? M is 2 times 9.8 equals to 2 times A, which is going to be 2A. So T minus 19.6 equals to 2A. That is equation number what? Number 2. So tension, remember, is equal, right? So I can make T the subject of the formula. So T here is equals to 2A plus 19.6. Here it's going to be what? Negative T equals to HA minus 40, which is the same as T equals to negative 8A plus what? Plus 40. Okay, so I'm multiplying by T, negative 1. So negative 1 times negative is positive. So this one will be negative. This one is also going to be what? Negative, because it's going to be positive because it was negative before, right? So T1, T2 is the same. So T1 is equals to what? T2, right? Which is the same as negative 8A plus 40 equals to 2a plus 19.6. 2a plus what? 19.6. So is negative 8a. So it's going to be what? Negative 8a minus 2a. I'm grouping the like terms. Equals to 19.6 minus what? Minus 40. So it's negative 10a here. 19.6 minus 40. 19.6 minus 40 is negative 20.4. Divide by negative 10. Divide by negative what? Negative 10. So therefore our a will be 20 divided by negative 10. It's 2.04 meters per second what squared. They are looking for the magnitude. So it's 2.04 meters per second squared. Right. So some learners will ask me why we didn't use the tension that we got. Remember, that was tension when an object was moving at a constant velocity. Now this object is what? It's accelerating, which will also affect the tension there. So hence I didn't use the initial what tension. So that tension was tension when an object was moving at a constant velocity. Then now what will be tension when an object is accelerating? We don't know. So hence I left t as it is, but that t for object that is acting on object 2 kilograms and object 8 kilograms, they are equal but acting in opposite what directions. Ne? They are also looking for what here? Tension. You can see, right? So they're also looking for tension when now an object is accelerating. That tension that we calculated in 4.3, it was tension when an object was moving at a constant velocity. Now we have a new tension after now an object is being it's accelerating. Ne? So what will be tension? It's simple. Take one of the equations. Remember we said t is equals to what? 2a plus 19.6. Right? So t will be 2 into 2.04 plus what? 19.6. So 2.4 times 2, it's 4.08 plus. Okay, so it's 2 times 2.04, which is 4.08 plus 19.6, which is going to be sorry about that, 2.04 plus 19.6. Yeah, so it's 23.68 what newtons. Then we get what? 2 marks. All right. So these are the answers, which I believe they're the same as ours. So this is what we did. We got this 19.6. We got this 19.6 for 4.3. And then we got this 2.04 meters per second squared for 4.41. And then 23.68 for what? For 4.4.2. Then this is an electric circuit. So let's look at this question quickly. Then in the circuit diagram below, the resistor R with the resistance of 5.6 ohms is connected together with a switch, an ammeter, and a high resistance voltmeter to a battery with an unknown internal watt resistance. There's an internal resistance here. The resistance of the connecting wires and the ammeter may be ignored. All right. So the graph below shows the potential difference across the terminals of the battery as a function of time. So this is how our circuit is connected. We have the resistor of 5.6. We have a battery there, or a cell. Are we given its EMF? Let's just check. For now, no. We are also not given, so we don't have EMF, right? We also don't have internal resistance. We have the resistance of it, which is 5.6 watt, 5.6 ohm. Then let's look at the circuit for now. The switch is open for now, right? So before we look at that statement below the circuit, so the switch is open. So when the switch is open, right? One, the reading on the ammeter there, because there's no flow of current, the reading on the ammeter will be 0 watt, 0 amperes. All right. So the potential difference across this resistor is going to be what? 0 volts. because I mean what the current that is passing through it is what it's 0, which means that even the potential difference across that resistor is going to be what 0 volts, right? What will be the reading on the voltmeter, right? Remember, there's no flow of what of current. Internal resistance here is not ignored, it is there, right? Right, so this voltmeter is going to measure what I want to say to you is this, learners. If the voltmeter is connected across the terminals of the battery, as shown in the diagram, it measures two things, right? One, it measures what the EMF. It also measures what the external potential what difference, right? External potential what difference. It measures the EMF if there is no flow of current, okay? So if there is no flow of what of current, then this voltmeter is going to measure what the EMF of the cell or the battery, right? But if there's flow of current, there will be a voltage drop. What causes that voltage drop is the internal resistance of what of the battery, okay? So if, for example, the EMF that was measured when the switch is open, let's say it was 12 volts, right? Then when the switch is closed, this voltmeter reading will what? Will decrease. Maybe let's say it decreases by 2 to what? To 10. So what is this 12? Is EMF, which is the potential difference across the terminals of the battery when there is no flow of what? Of current, okay? But how do we define EMF, learners? Remember, it is the maximum energy a battery can deliver per unit charge passing through it, né? Okay? That is the EMF, right? So that is the maximum energy a battery can deliver per unit charge or per coulomb of what? Of charge passing through it, okay? So the voltmeter, when it is connected across the terminals of the battery, it measures two things. The EMF when the switch is, when there's no flow of current, right? And two, it measures the external potential difference when now there's flow of what? Of current. So when the switch is open, maybe you'll get 12, right? When it's closed, it will decrease maybe from 12 to 10. Why there is that voltage drop? It's because of the internal resistance of what? Of the battery. And what is this 10 now? It's no longer the EMF. It is what? The external potential what? Difference. So I hope it's clear. Right. So we are given the graph. Okay. So what are they saying here? At time T1, switch is what? Is closed. Here, the switch now is what? Is closed. It was open here. So if it's opened, it measures what? The EMF. Okay? Then if it is closed, there will be a voltage drop, right? And that reading now, it's no longer going to be the EMF. It is going to be what? The V what? External potential what? Difference. So I'm having the EMF, I'm having the external potential what? Difference. And if I'm having the EMF and the external potential difference, I can also get the internal potential what? Difference or lost volts. So EMF, remember, is given by V external plus what? V internal. EMF, if the EMF is 13, it is 13 in this case. It's what is given, right? V external is 10.5 plus V internal. So my V internal will be 13 minus 10.5. So what is 13 minus 10.5? Is 2.5. So I'm having 2.5 volts for the internal what? Potential what? Difference. But when the voltmeter is connected across the terminals of the battery, it measures two things: the EMF if there is no flow of current, external potential difference if there is what now? Flow of current. And the EMF is always greater than the external, right? So immediately when there is flow of current, there will be a voltage drop because of the internal what? Resistance. So then you will have the V what? External. Then please, learners, again, be careful when they ask questions. They will say, when the switch is open, right, the voltmeter, which is connected across the terminals of the battery, reads 13 volts, right? Or the reading on the voltmeter is 13 volts. Then now when the switch is closed, the voltmeter reading decreases by 2 volts, for example. If they say decreases by 2 volts, that 2 volts now is going to be what? The internal potential difference. Decreases by, when the switch is closed now, the reading on the voltmeter decreases by 2 volts. So that 2 volts will be the what? The internal potential what? Difference. But if they're saying decreases to, right? So decreases to 10 volts. That 10 volts will be the external potential what? Difference. So the issue of language there, let's be careful. Be careful when it comes to that, learners. Ne? So the reading on the voltmeter when the switch is open is 13 volts. That is your EMF. When the switch is closed, the reading on the voltmeter decreases with 2 volts, decreases by 2 volts. That 2 volts is the internal potential difference. Decreases to 10 volts. That 10 volts will be the V external, or the external potential what? Difference. Okay. So here we have EMF, we have V external, we have what? V internal. All right. So define the term EMF of the battery. EMF of the battery, that is the maximum energy a battery can deliver per unit charge passing through it. Ne? Then that is how we have to define EMF according to your exam guide. Write down the value of the EMF. So the EMF will be, they just want the value. So you can't say 13. Oh, they're saying the value. Yeah. So if they say the value, even if you wrote 13, it's still fine. But actually it should be 13. So here they were supposed to say magnitude. Ne? So it's 13 volts there. Right? Then when the switch is closed, calculate the current through resistor R. Ne? So the current through resistor R is equals to V over I. What is R? R is 5.6 if I'm not mistaken. Yes, it's 5.6. So we are looking for what? The current. What is V? V is external potential what? Difference. Ne? So the potential difference across this resistor, initially it was 0 when the switch was open. But now it will be what? 10.5. It's what is given. Ne? So it will be 10.5. So here is 10.5 divided by I. My I here will be what? Will be 10.5 divided by 5.6. Which is equals to what? 10.5 divided by 5.6, which is 1.875 watt amperes. The issue of units there is very, very important, learners. Okay? Then power dissipated in resistor R. Power dissipated in resistor R. Already for resistor R, I'm having the resistance, I'm having the current, I'm having the potential what? Difference. So I can use P equals to VI. My V is 10.5. My I is 1.875. Right? I can also use P, and it is P equals to VI, right? Which is 10.5 times 1.875. Okay? I can use P equals to I squared R, which is going to be 1.875 squared times 5.6. I can use also P equals to V squared over R, which is equals to what? 10.5 watt squared over R, which is 5.6. So I must get the same answer here in watts. So I can use any, right? So what is 10.5 times 1.875? So here I'm having 19. I'll round off it to 2 decimal places. I'm having 19.69. Even here it should be 19.69. 19.69. So that is our power dissipated by the resistor R. Okay, last question, internal resistance of the battery. So the internal resistance of the battery, from the data sheet we can use E equals to I open brackets R plus small letter r. I is the total current of the circuit, which is 1.875. What is the EMF? Is 13. Okay. What is R? That is external resistance. In the external circuit, we are only having one resistor of 5.6. We are looking for small letter r. Yeah? I'm having, I can divide by 1.875, divide by 1.87175, then this and this. So I'm having 13 over 1.875 equals to 5.6 plus r. Then I can have 13 this side over 1.875 minus 5.6. This will be equals to what? R. Ne? So what is 13 divided by 1.875? It's 6.9333 minus what? 5.6. And then the answer here is R equals to 1.33 what ohms. Then we are done, or we have calculated what the internal what resistance, or we can use what R, okay, this one V equals to I times small letter r. V, that is internal, or V lost, which is what? 13 minus 10.5 equals to total current 1.875 times what? Times R. So what is 13 minus 10.5 is 2.5 equals to 1.875 times R. Divide by 1.875 divide by 1.8 what? 75. Then our R here will be 2.5 divide that by what? 1.875. And that is going to be 1.33 what? Ohms. So it's another method that we can use to calculate our internal what? Resistance. I think we have tried our level best to do, although we didn't cover all structured questions, but based on the multiple choice questions, we have tried to cover other, topics or other concepts when it comes to our paper 1. I think for today it's enough, learners, and I hope you have learned something. And come next week, the focus will be a paper 2 what? A revision. So these are the answers here, and then next week then we'll focus on what? On our paper 2. Thank you so much for watching this lesson. See you next time. Bye bye.